Well, we have learned of the physics definition of heat, that heat is energy transferred because of a difference in temperature. This video will discuss three methods of how energy is transferred from one location to another. And those three are conduction, when we have one end of a material hot, the other end cooler. Heat will be conducted, energy will be conducted, I should say. If we create some flow of hot material, so we can have convection, hot material moving from one place to another and physically carrying the energy, the more energetic particles, to another location. Then we can have radiation. Light carries energy from one location to another. So conduction, where we have physical contact between the two different temperature regions. We have convection, that takes, by mass motion, takes the more energetic material to a location that has less energy. And we have radiation, light carrying energy. It is good practice to insulate the walls of the home to prevent too much loss of energy in the winter. So we're taking a look at material here that has a low conductivity. It does not conduct energy well from one side to another. The process of this transfer of energy is shown here, where we have some barrier. And if we say this is a winter example, inside the house over here at higher temperature, the molecules travel at faster speed. They're more energetic and energize the wall material. And then the actual conduction takes place with electrons, usually, conducting the energy from one location to another. But on the far side, where there's a region of lower temperature, the molecules, as they bounce off here, can bounce off with more energy. They've picked up some energy from the wall. So that would be one version of heat conduction. Another version is the transport of energy by the motion of electrons through the material. So here we go with thermal conductivity. If we have a metal, thermal conductivity will be high. The situation is that in a metal, approximately there's one free electron per atom, and that electron can carry kinetic energy easily across the region where the material is located. So this thermal conductivity, what are some things that would increase Q? Q is the value of the heat, the energy that's being transferred from the hot region, T2, to the cooler region, T1. What are some factors that would increase Q? Well, as I said, if we have a metal here, where the electrons are more easily able to carry kinetic energy across the material. So the thermal conductivity is one factor. If the conductivity goes up, the value of the energy will go up. If we have a longer time, if this is this temperature difference is existing for 10 hours, that will lead to a higher Q than if it's just 1 hour of a temperature difference. Area, if there's more area, then more energy will be able to get from one region to another. So that would increase the situation that we have. What about distance? If the two regions are separated by a greater distance, we've got this conducting material that the energy has to go through, will that lead to high Q or low Q if this distance is large? And it leads to low value of Q. It's harder for the energy to get across to the destination if there's a longer distance, physical distance, to cover, to deliver that energy. So the Q number will be bigger if the conductivity is bigger, if the area between the two regions is bigger, and if time is larger. And the Q will be smaller if the distance is greater between the two locations. So that's thermal conductivity and the way the energy calculation proceeds. Then one last feature here. Do you think Q will be higher if T1 is 10 degrees Celsius higher than T1? Or if T2 is 50 degrees Celsius higher than T1? And the answer is Q is higher if the temperature difference is greater. So there are those four factors that increase Q. The conductivity, if that's higher, Q is bigger. If the area of contact between the two regions is greater, then Q will be greater. If the temperature difference is greater, Q will be greater. And if the length of time over which this temperature difference exists is greater, then Q will be greater. And what decreases Q? Having a thicker barrier between the two regions. Thicker barrier. So fiberglass can be used effectively for insulation. It has small pockets of air, and air by itself is not a good conductor. And if these are pockets of air, then convection is prevented, and you make it thicker in order to cut down the Q value between the inside of the house and the January weather conditions outside. Okay, convection. With convection, we have energy in some region that can physically move. So we're talking about a liquid or a gas being involved with convection. And the furnace is running here just under the influence of gravity. There are homes that operate like this, where the hot air rises and then goes back down through the home back to the furnace that might be in the basement or at least on the first floor. But taking advantage of natural convection, this hot material is less dense. The hot material, the molecules bump against each other harder and take up more space, so the material is less dense and it naturally will rise. The other way this is usually enhanced to deliver energy is to put a fan and ductwork on the system and push the air, the hot air, to the place where you want to deliver that extra energy. But that would be convection. Boiling something on the stove, the water, as temperature goes up, it becomes less dense, and we have, we're talking way above 4 degrees Celsius here. But as the temperature goes up, the water becomes less dense, and we get natural convection taking place. Another illustration of insulation here with fur, creating pockets of air that block the energy transfer, at least minimize the energy transfer. They don't totally block it. Convection occurring here as the water goes from vapor back to liquid. What's true about the energy situation? Is energy released when water goes from vapor to liquid, or is energy required to make water go from vapor to liquid? And you should be recalling that energy is required to go from liquid to vapor. So when the water condenses in the cloud, there's actually energy released and makes the air lighter, warms up the air, makes it lighter, and you get thunderheads that grow and rise to a greater height as the water vapor goes into a liquid state. This can also lead to friction between the atoms and molecules and separation of charge, and then the lightning occurs. Phase change being illustrated here as the iceberg is in water that's warmer than 0 degrees Celsius. And again, that's a large amount of energy being involved with a big mass like this. It cools down the water, and the energy that comes out of the water goes to changing the phase of the iceberg. So here's radiation. If you hold your hands in front of a fire, not too close please, but hold your hands in front of a fire, you can feel energy coming into your hand by virtue of the light. And the infrared light is effective. It's not just the visible light that you see, but the infrared light coming from the fire is effective at warming your hands. Objects do emit different wavelengths of light as a peak of the spectrum at different temperatures. So an object that's 3000 Kelvin will appear red to us, to our eye, because it does not emit much blue light. And the spectrum here from blue on one end to red on the other end, at low temperatures, 3000 Kelvin is not a low temperature necessarily, but for the numbers that are given here, the smallest temperature is going to result in a spread of energy versus wavelength graph that has a peak out in the infrared. It does turn out that objects emit light at all wavelengths, but there's a certain peak wavelength that's related to the temperature of the object. As the temperature goes up, this peak of this curve shifts to a smaller wavelength. So 4,000 Kelvin, we're getting more energy at every wavelength, but notice the peak is shifted to the left. And at 6,000 Kelvin, this is essentially the characteristic temperature of our sun, the outer layers of the sun, where the light comes from. Not the core, but the outer layers. So 6,000 Kelvin, white hot, because we're getting energy at all the wavelengths, red through blue, and as all those colors mix together, our eye perceives that as white. But red hot at the beginning here, so if you're watching a blacksmith at a historical event or celebration, recreation of a blacksmith working with iron in a charcoal fire. As that iron gets warmer, you see a dull red glow and then a brighter red glow, and then if it's really hot, it could be white hot. And that high temperature results in the body emitting light at significant energy at all the colors. This 3,000 Kelvin curve, it's still emitting blue light, but just not nearly as much as the energy in the red light, so it appears red to our eye. But as the temperature goes up, a solid, a liquid, or dense gas will emit energy at all wavelengths with greater energy as the temperature goes up. And then the peak energy wavelength, the wavelength where the peak energy exists on this graph, shifts back to the shorter wavelengths. So with a telescope, you can see this with stars. There are certain red stars that are cooler on their surface, and there are blue stars that are very hot on their surface. So we have that illustration. As far as absorbing light, black works better than some shiny material or white material to absorb radiation. So sunlight here works best on the asphalt first and on concrete later as far as raising its temperature. In terms of reflection of light, this technically is called the albedo, on how much light is reflected. It turns out that, of course, black is going to absorb more than silver, but it also turns out that black is better at emitting light than silver. So the blacks absorb better, but they also emit better. A house photographed with infrared wavelengths, and where it's brighter in the infrared, showing where there's energy loss that the homeowner or the hotel owner, whoever owns this massive building, would need to pay attention to, or the army barracks. Solar oven. If you can build with aluminum foil a box with plexiglass across the top here, and you can cook things with a solar oven. And especially in third world countries where electricity is not readily available, items can be cooked with solar energy. It's radiation from the sun carrying energy to finally get absorbed in the black cooking vessel that's there. A dewar, a thermos bottle, is built to minimize the flow of energy from the inside to the outside. So it'll hold a hot or a cold liquid. But let's say it's holding a hot liquid, so coffee, perhaps hot chocolate. There, in a thermos bottle, a dewar arrangement, there is a dual wall, a double wall container here with vacuum in between, meaning the air molecules have been evacuated, so there's no air to carry energy from one wall to another. So that reduces the flow of energy. And then just light contacts between the glass wall and the outer shell, again, not giving much opportunity for the movement of energy. Having a small area will lead to a small cube. And then the container itself and the silver wall, having silver on it reduces the radiation. If we would have a clear flask out to the outside world, then the temperature would increase quite a bit. Light would carry energy away from this object, if it's hot, to the outside world. But having a silver coating on this thermos bottle reduces the amount of radiation energy that's carried. So this device built to minimize the movement of energy from the hot region to the cold region. For the Earth, we have sunlight coming in. Some of the light does reflect off of clouds and off of ice. About 30% reflects. The Earth absorbs about 70% of the available sunlight. So the Earth receives that. The Earth has a temperature where the light that the Earth emits is in the infrared. And it does turn out that there are gases in our atmosphere that absorb in the infrared. There's carbon dioxide, there's water vapor, methane, and when they absorb, they re-emit, and a lot of the energy they re-emit comes back down to the Earth, increasing the temperature of the Earth. This is the greenhouse effect. Our Earth has a certain equilibrium temperature. We absorb energy from the sun. Not all the infrared is blocked by our atmosphere. There's a good portion of infrared that gets out into space. And there's a balance. The energy coming in and absorbed equals the energy going out that keeps the Earth at a certain temperature. If for some reason we would block more of the infrared light from leaving, that energy would come back to the Earth. Eventually, the Earth must radiate as much energy as it receives from the sun. And the way to accomplish that is for the Earth temperature to increase. When the Earth's temperature increases, it emits more energy at every wavelength. And there's a certain fraction that gets absorbed by the greenhouse gases, carbon dioxide, water vapor, methane. But if they were emitting more energy, then eventually the amount of energy that gets through the atmosphere will match what comes in. But that's going to require the Earth to have higher temperature. So that's the greenhouse effect. And the greenhouse effect, I should let you know, is not all bad. Right now we have a global average temperature somewhere around 59 degrees Fahrenheit. And if we had no greenhouse gases in our atmosphere, our temperature would be about 50 degrees Fahrenheit lower. The greenhouse effect that we have right now gives us a global average temperature about 50 degrees above what we would have if we had no atmosphere. So the greenhouse effect does make life a little bit more easy to get by, especially during the winter, compared to if we didn't have a greenhouse effect. Another way you can kind of key in or relate to this greenhouse effect: what nights in January are the coldest? What nights in January are coldest? The clear nights or the cloudy nights? And it's the clear nights that are coldest. When the sky is clear, free from clouds, not as much water vapor, then the infrared more easily gets out into space. But if the clouds are present, that's going to absorb more infrared and send that energy back to the Earth, keeping us somewhat warmer on that night. The clouds act like a blanket and keep us from having a lower temperature than you otherwise would. Well, we have an okay greenhouse effect right now, but it may not be okay in the future. We may have an increased greenhouse effect that we don't want. So here are actual measurements of carbon dioxide in our atmosphere going back into the 1950s. And there's a seasonal effect. There's more land mass in the northern hemisphere. So when the northern hemisphere has summer, we have grass and trees, etc. And those plants are removing carbon dioxide from our atmosphere in a measurable way. So the bottom points here, that's summer in the northern hemisphere. And then in winter in the northern hemisphere, we don't have that plant activity. There's not as much carbon dioxide removed from the atmosphere, so we get a higher level that's measurably higher than in the summer for the northern hemisphere. There is a trend. Carbon dioxide levels are increasing and headed, an increasing level of carbon dioxide. It's accelerating. And one reason for this would be that we're burning fossil fuels that releases carbon dioxide into our atmosphere. So that's a concern. Temperature measurements do have some relationship to the amount of carbon dioxide in our atmosphere. So this is a really expanded scale. But we see here the global temperature, and we see a rise in the temperature. The histogram, the rectangular bars, are the temperature, and the black line is the amount of carbon dioxide in our atmosphere. So there is a correlation. It's something of great scientific interest as to how much cause and effect there is between the carbon dioxide and the temperature. When we drill ice cores in the Antarctic, we can get information, scientists can get information on how much carbon dioxide was in the air in the past. There are bubbles trapped in the ice that can be analyzed for how much carbon dioxide is present. And there are indicators of temperature also in the ice that can be identified. So we have a graph here. It again shows a relationship. There are natural variations of carbon dioxide in our atmosphere. However, you'll notice that they're down around the 250 parts per million, and we're up to getting towards 400. We've increased the amount of carbon dioxide in our atmosphere to a great extent after the Industrial Revolution and burning coal, burning oil, and so forth. And then a little bit more on energy. Nuclear power plants have spent fuel rods that continue to create energy from radioactive decay in those fuel rods. It does take a long time for the material to cool off because it's releasing energy still, not as much as if it was active as part of the core of a nuclear power plant, but there's still long-term half-lives that cause energy to be released. How does a walrus live on ice? Well, it's got a built-in insulator with the layers of blubber, and those keep the interior of the walrus from losing energy too rapidly to the ice. Lava, you can see it emitting light because it's hot. It emits quite a bit of light compared to the rocks around it because it's hotter. So there we have a little tour of transfer of energy from one place to another. Conduction, and for my students we'll do some calculations with that. Convection, the mass motion of material, very difficult to do calculations with that because the material's losing energy all the way along as it moves from point A to point B, and there's a lot of turbulence in the interface between the hot material and the cooler material, so we won't do any calculations with that. Radiation, the calculations are not too difficult. For my students, we won't be doing those. But we have three methods by which energy can go from the hot region to the cooler region. We have conduction. Again, the electrons are a key component in carrying kinetic energy from one place to another. We have convection, where the hot material physically moves to a new spot and carrying the energy with it. And we have radiation, light, carrying energy from one place to another. So keep reading and asking questions.